All right, everybody quiet. Everybody paying attention. I'm going to cut the screen on. Okay. All right. So, today, what we're going to look at, 5.8 and 5.9 basically go together. It's putting together all of the things that we have looked at. And it's going to pull back in some things that we did in pre-calculus, although I think there's at least one there that I didn't do in pre-calculus. I used to do it in pre-calculus. So what's kind of cool about this is that you can actually get a pretty good picture of what a graph looks like using everything that we have learned, putting all of that together. We're only going to do one where we do like the complete curve sketch where we find everything about it, and then we'll look at some other problems that are a little bit more like what you'll see on exams, because a complete curve sketch takes a while to do because you need all kinds of things. You need x-intercepts, y-intercepts. You can use symmetry. We did not do symmetry whenever we were in pre-cal because they have taken that out of the curriculum in North Carolina. But we might talk about it, or we might just decide not to worry about it. Domain, range, continuity, we learned about in these sections here. Vertical asymptotes, differentiability, relative extrema, we just talked about. Concavity, horizontal asymptotes, these are all things that we have looked at here. So knowing all of this stuff, we can sketch a graph. So we're going to do that for one problem. It's going to take us a while to do for one problem. Most of the stuff you're going to see that actually makes it on the exam will not ask you to do the whole entire curve sketch because it does take a very long time. But I think it is kind of cool. Now, this chart right here, I draw often to help me remember how everything relates, right? So if we know a derivative is positive, what does it tell us about the function? It is increasing. And if we know that a derivative is negative, it tells us that that function is decreasing. This is always true. So if we know a second derivative is positive, it tells us the first derivative is increasing. And if we know a second derivative is negative, it tells us the first derivative would be decreasing. So, if our derivative or our rate of change is increasing, that is concave up. And then here we would have concave down. So the first derivative tells us about whether the original function is increasing or decreasing. The second derivative tells us about whether the original function is positive or is concave up or concave down. All right. Now, we will be asked questions about this. Sometimes we'll be asked to take the derivative and tell about the original function. Sometimes we might be given the original function and be asked about the derivatives or second derivatives. And we'll see some different questions like that. So it depends on what you have information for. So let's say that they give you a picture of a first derivative, right? Maybe you have a graph or a table. Maybe you don't have the equation. So if you have a first derivative, if that first derivative is positive, which would mean above the x-axis, right? Or obviously in a table it'd just be a positive number. Then that tells you that the original function, the f of x that you're not looking at, that function would be increasing. So if they give you a graph or a table they are hardly ever actually asking you about the function you're looking at. So if you are given a picture of f prime and it's above the x-axis, you may want to put that there, above x-axis. Positive would be above the x-axis. Then that would tell you the original function is increasing. And then negative if you see that first derivative is below the x-axis. Right? And so it just depends on what you're given information for. Perhaps they give you a picture of the original function. They give you f of x, and you notice that f of x is concave up. They might ask you a question about the second derivative in that case. So if you see that the original is concave up, then the second derivative would have to be positive. So it just depends on what they have given you. Sometimes we'll be asked like to find the second derivative and tell what the original looks like. Sometimes we're asked from the original what the derivatives would look like. But you're almost never asked, here's the original, tell me what the original looks like. You know, like they won't usually ask you about the one that they've actually given you. Does that make sense? Because that could be done without knowing how to do any calculus. Okay, so here's our big curve sketch problem. This is going to take us a little while to do. We're going to find everything we can find about this particular function. Okay, so we're going to go back even all the way back to pre-cal and just think about what we can figure out about this. So let's do x-intercepts. How do we find x-intercepts? What is it? Y equals 0. So plug in 0 for y. So for this one, that'd be 0 equals 2x squared minus 9 over x squared minus 4. But really, the numerator is all that matters here. So if you divide by 2, you still get 0 equals x squared minus 9. You move your 9 over, and you get plus or minus 3 for your x. So our x-intercepts would be at 3, 0, and 0. I'm sorry, not 0, 3. Negative 3, 0. So that's one piece of information that we know. So if we're graphing this, we can go ahead and plug in, you know we got dot set 3, 0, negative 3, 0. Okay, let's do our y-intercept. What do we do for y-intercept? X equals 0, so plug in 0 for x. So f of 0 would be 2 times 0 squared minus 9 over 0 squared minus 4. This is going to give me negative 18 over negative 4, which will be 9 halves. So my y-intercept is going to be at 0, 9 halves, or 0, 4.5. Okay, we could talk about thinking about the domain, or we could talk about vertical asymptotes. In this case, they're kind of one and the same, right? So if I'm looking for vertical asymptotes, where are those going to happen? Vertical asymptotes. Bottom equals 0 and does not cancel with the top, right? Because if it cancels with the top, what do we have? Whole. Is anything going to cancel with the top here? No. So vertical asymptotes. And I'll put a short little summary here so we remember. So, bottom equals 0 and does not cancel. With top. So in this particular case, x squared minus 4 would equal 0, so that'd be x squared equals 4, and we'll get x equals plus or minus 2. So we get vertical asymptotes at x equals 2 and x equals negative 2. Okay, that's also our domain here is that x cannot equal 2 and x cannot equal positive. X cannot equal negative 2 and x cannot equal positive 2. Okay, everybody okay finding everything so far? All right, what about horizontal asymptotes? How do I do those? Horizontal asymptote. Horizontal asymptotes. Good. Bobo-Botno. And when we're doing Bobo-Botno, because especially we're in calculus right now, if you have something for response and you're asked to find horizontal asymptote, you're going to have to, have something a little more specific than Bobo-Botno. We use Bobo-Botno for limits as x approaches infinity or negative infinity, right? Because we're horizontal asymptote, so what's happening out here is your x gets bigger and bigger. You're getting closer and closer to a particular value, right? So you're going to do limit as x approaches positive or negative infinity of f of x. And to do that, you can usually use Bobo-Botno. But if it's free response, you need to use limit notation for that, or they won't give you full credit for that. So in this case, we would be looking at the limit as x approaches infinity of, what was our function? 2x squared minus 9 over x squared minus 4. And what do we have here? Bigger on bottom, bigger on top. Exponents are the same. Exponents are the same. Because you could distribute that 2 right there, but you still just have x squared on top and bottom. So exponents are the same. Divide coefficients. So we're just going to get 2 over 1, which will give us 2. Would this be any different for negative infinity? It would not. The only time that you guys will see where it's different for negative infinity is if you have square roots or exponentials, or places that you will see those be different. So we have a horizontal asymptote at y equals positive 2. So that's another piece of information that we want to know. All right, so we got x-intercepts, we got y-intercepts, we got vertical asymptotes, we got horizontal asymptotes. I don't think there's anything else we need to know before we start doing like our, this is calculus, but like our real calculus, our increase and decrease and stuff. Let me see. We can think about continuity. It kind of goes hand in hand with these vertical asymptotes because that's kind of in with our domain as well. So a function like this should be continuous everywhere except for at those vertical asymptotes. So that is important to think about as well. But I think we're ready to start doing derivatives and think about increasing and decreasing. So our function, I think it'll be a little bit easier to take our derivative. So increasing and decreasing we're going to look at sine of our first derivative. So I would probably do f of x. I'd go ahead and distribute that too. So you got 2x squared minus 18 over x squared minus 4. So to take this derivative, we're going to have to use a quotient rule. So we would have x squared minus 4 times the derivative of the top, which would be 4x, minus 2x squared minus 18 times the derivative of the bottom, which is 2x, all over x squared minus 4 squared. We can simplify here. 4x to the third minus 16x. And then we'll get minus 4x to the third plus 36x, or x squared minus 4 squared. And that is going to be, the 4x cubes will cancel. I'll get 20x over x squared minus 4 squared, I think. Double check my work on that. Because this gets distributed here, and your negative is also distributed, so I think I feel that right. Okay, so we could do a sign line for this. To do that, we need to have, we'll set 20x equal to 0, which is just going to give us x equals 0. We'll also set x squared minus 4 squared equal to 0, which is just going to give us x squared equals 4, which will give us plus or minus 2. So if we do a chart here, we'll have 20x, we'll have x squared minus 4 squared. We'll get our answer for f prime. So we got negative 2, 0, positive 2. And x squared minus 4 squared, always positive because you're squaring it, right? Can equal 0, but as far as our intervals right here, it's going to be positive everywhere. And then, so 20x is really all you're looking at. You'll get a negative here for these two and positive here. So yes. Mm-hmm. No, you cannot square it like that because you would have to write it like this. X squared minus 4 times x squared minus 4. Like that. So you cannot just square both of those. You would have to do this, which would give you, like, you get x to the 4th minus 8x squared plus 16 if you did it that way, which is going to make it more difficult to solve rather than easier. So what I did there, to get rid of that square right there, you can just square root both sides, which will just give you, I didn't write that step, but it'll give you x squared minus 4 equals 0. Then you just move the 4 over. Yeah. Okay, other questions? All right, so let's make some conclusions about what should be happening here. So we should be decreasing on negative infinity to negative 2 and negative 2 to 0. Actually, I should probably use brackets there. Actually, no, on this one, you've got vertical asymptotes there, so let's not use brackets. The reason it needs to be broken up is because you're going to have a vertical asymptote at that negative 2. So at negative 2, it's not defined, so nothing's happening there, so you wouldn't include it. And then we would be increasing then you could combine, yes. Yeah, if it was continuous at that point. So then we would have from 0 to 2 and 2 to infinity. Oops, I should have a negative right there. And if I want, I also could go ahead and say that I should have a relative minimum at x equals 0. And actually, at x equals 0, that's also your y-intercept, right? Which we found up here was 0, 9, 2. So that's our y-intercept, which was at 0, 9 halves. So we've got all this information that is helpful for drawing. The only thing we don't have information about right now is concavity. So for concavity, we need a second derivative. Right? You can see why I'm not going to make you do this completely a lot, because it's a lot. It's basically taking like everything we've done and putting it all together in one problem, which is going to be extensive. So for concavity, we need to look at the signs of the second derivative. So to find that second derivative, our first derivative is up here, so we would need to use quotient rule for that. So we would have x squared minus 4 squared times the derivative of 20x, which is just 20. Then we would have 20x times the derivative of x squared minus 4 to the second power. You've got to use chain rule right here. So you've got 2x squared minus 4 to the first power times the derivative of the inside, which is 2x. And all of that would be over x squared minus 4 cubed. All right, so, oh, I'm sorry. I was thinking ahead to what is going to happen, I think, here. Would be to the fourth right there. So, if you'll notice right here, I've got this stuff right here matches with this stuff right here. So I can factor the lowest one of those out, which will cancel with one of the ones in the bottom. All right? So that is going to be the simplest way to simplify, because otherwise you got to square, double square this, and then distribute and everything, and then you might need to factor back out to get something to cancel. So since I've got x squared minus 4 with both of these, I could factor one of those out. So if I take it out of this first term right here, I would be left, the 20 would still be there, and one of the x squared minus 4s would still be there. So when I take out the x squared minus 4 here, this is what I'm left with. And then in that second term, if you take out the x squared minus 4 right here, there's just one of them, so it's gone. And that leaves us with 20x times 2 times 2x, which is going to give us 80x squared. So this x squared minus 4 is to the first power. We can cancel it with one of the ones down here because we've got 4 of them. So I'll make that to the third power. And so that's going to give us 20x squared minus 80 minus 80x squared over x squared minus 4 to the third power, which would be negative 60x squared minus 80 over x squared minus 4 to the third power. Okay, questions? All right, so if we look at this, we got to look at numerator and denominator equal to 0, so negative 60x squared minus 80 would equal 0, and then we've got x squared minus 4 to the third power would equal 0. And so over here we got negative 60x squared would equal 80. And then divide by negative 60, x squared is going to be negative 4/3. What's going to happen when we square root that? You'll get i's. So that you don't get any values from that. Over here, we would cube root both sides. That would give us x squared minus 4 would equal 0. Here we'll get x squared equals positive 4, and x equals plus or minus 2. And so for our sign line, for this we would just have negative 2 and positive 2 here. We got negative 60x squared minus 80 in our numerator. We've got x squared minus 4 to the third power in our denominator, and then we're looking at the second derivative. Okay, I didn't get any zeros for this, which tells me that I probably always positive or always negative. What am I going to get for negative 60x squared minus 80? It's always negative, right? No matter what number you plug in. If I plug in negative 3, I got negative 60 times negative 3 squared, which is 9. That's a really big negative number. Minus 80, still negative, right? I'm going to get a negative here. I'll also get a negative here. So you get negatives all the way across for that one. For the second line, if you plug in a number like negative 3, you would get 9 minus 4, which is 5. And then if you cube that, you would just get 5 cubed, which would still be positive. But if you pick a number between negative 2 and 2, like 0, you get negative 4 cubed, which is going to be still a negative number when you cube it, because odd powers are still going to retain that negative. And then over here you'll get a positive, so you get negative, positive, negative. So if we make our conclusions here, we should be concave down for negative infinity to negative 2 and 2 to infinity, and concave up for negative 2 to 2. They don't do it quite as much as they used to, but they definitely used to a lot. Basically make this one big free response question. They'd ask you several different things about the function, and then the last thing would be to sketch the graph. They still take a lot of aspects of this and put them on free response questions, but I have not seen one in several years where it asks you to do all of these parts, because they've got to where they like to make you both take a derivative and integrate on the same problem. Yeah. But we still need to sketch a graph of this. So, all right. I'm going to pull up, we're going to put a graph up here. Well, I guess I'll sketch it by hand so that, because that's what you guys are going to have to do. So, all right. I know I need to go, let's see. I know my y-intercept was at 4 halves. I know my x-intercepts were at 3 and negative 3. So I'm going to go out to like 5 or 6 on each axis. Okay. All right, so it's all about to come together. Everything we've learned, we're going to be able to create a beautiful graph that's going to be fairly accurate here. So let's see, we did x-intercepts. We're at negative 3 and positive 3, so I'm going to put some points there. My y-intercept was at 0, 9 halves, so 0, 4.5 right here. This is not part of the graph, so I'm going to draw it with a dotted line. But I had vertical asymptotes at, what was it, 2 and negative 2. So I'm going to draw those with a different color and a dotted line, because that's going to be a barrier to my graph. And another one over here. 2 and negative 2. What was my horizontal asymptote? 2. All right, so okay. All right. So we can kind of look at these in sections now, from basically from -2, 0, and negative infinity to -2. I should be, my first derivative is negative, and so that's decreasing, and my second derivative is negative, so decreasing and concave down. So when I draw this in, and I've got a horizontal asymptote here, so I need to get closer and closer and closer to that line. And I've got a vertical asymptote here, there. And then in the middle, from -2 to 2, I'm concave up. Second derivative is positive, it's concave up. I decrease and then I increase, right? From -2 to 0, I'm decreasing. From 0 to 2, I'm increasing. So concave up, decreasing to increasing, so it would look something like this right here. And then last, we are increasing concave down over here, so it's going to be kind of mirrored from the other side, like this. Now, you got to think of how important this was long ago, because Desmos did not exist. The TI-84 or 89 did not exist, right? Their like best graphing methods were like some plugging in and checking and like plugging in, plotting points sort of things. So knowing things about how the graph looked without having to plug in a bunch of numbers was really important. Now, we do have Desmos today, but we need to understand at least some of what's happening behind all of this to have a greater understanding of the way it all works together.
So if you wanted to actually get the slopes of the points, would you have to plug numbers in? Or is there a way to do that?
You'd have to plug in numbers to get the exact values.
What is
now,
the real world application?
This is mostly just understanding how all of this works together and what that means. We are getting to where we're going. So like the last section is optimization, and we're going to do some problems where we will see where this can be used in some real life places. So the main thing here is understanding how the first derivative and second derivative, what they tell us about the original function, and understanding how that kind of like all works together is the main purpose of all of this. So this is like obtaining a solid understanding, and then we're going to extend that to applying it to situations in the next section that we'll do. On the AP exam, if they gave you something like this, it would be a free response question, and it would be, you'd have like parts A, B, and C, and they'd ask you to find, A might ask you to find horizontal asymptote, B might ask you for increasing, decreasing, C might ask for something like points of inflection, and then D would ask you to sketch the graph. So they would never be like, here's this problem, do the whole thing, because as you can see, it's taken us like 20 minutes to do this, and so it might present itself in like an entire free response question where they're asking you these different parts and then ask you to sketch the graph, but you would not see this as like a single question. And they might ask you any of these parts on a free response or on a multiple choice, but you won't see all of it together in one like question unless it's a free response with the parts broken out. Okay, so why is example 2 blank? Is it blank on yours?
No.
What happened to it? It's there. What's happened to it? They're all gone. They were not the other day. I mean, I printed that off. Okay. We're going to close it and open it back up and hope that it shows up. Come on. Please. Okay. Okay. All right. So here's an example of something they may ask you. Okay. All right. So the first derivative of the function is given by this equation. Second derivative is given here. On what open intervals from -2 to 2 is the graph both increasing and concave down? Okay, so we're going to use the calculator on this, but I want us to think about what we will be looking for here, because you can do this a lot. You can do it much more easily. If you think about what you need first. You don't have to look at both graphs if you do this. So, if I know that H, it tells me that it is increasing and concave down. Okay? And this is going to be much like that we have filled in. If I know H is increasing, what does that tell me about the first derivative? Positive. Okay. Does it tell me anything about the second derivative? No. Nothing. All right. Concavity can actually tell me about both, but concavity, I typically think of it as a second derivative thing, right? If I'm concave down, what's my second derivative? Negative. Okay? But if my second derivative is negative, what does that tell me about my first derivative? That it is decreasing. So, if I just look at the first derivative, right? If I can see where H prime is positive, which on the graph, what's that going to look like? Above the x-axis. And decreasing. So when it's above the x-axis and decreasing, I don't have to look at the second derivative. I could, but I don't have to because I can tell both things from that first derivative. So that is going to be the easiest thing to do for this. So let me pull up the calculator here. And as nice as it would be to do this on Desmos, I'm going to do it on the 89 because we can't use Desmos on the... Alright, so 3 natural log of 2 plus cosine 2x minus x okay, and then we're only looking from -2 to 2, so I'm going to go to my window and I'm going to make this from -2 to +2 because I don't really care about anything outside of that. And I'm going to graph. If you do the green button and F2, it'll take you to the window. Okay, so I know you guys cannot do this. But let's think about where we're looking, what we're looking for here. We need the derivative, which is what I've just graphed, first derivative, to be positive and decreasing, both, right? So the sections where that happens is from here to wherever that minimum point is right there. And then, again, my maximum's probably somewhere here till I hit this x-axis here. Now, just based on the answers, I think we'd be looking at one of these two, right? And they're the same right here, so I'm not even going to look. Like, I could find this point exactly on my graph if I wanted to, but I can see those are both the same. Then I could find this point on my graph if I wanted to. I'll show you in a second, just in case you get one where it's necessary. I could find that. And which one does it look like, 1.085 or 1.656? I think it's 1.085. I think A is the answer. So if you're short on time, just reason through it, right? You don't have to actually find those points if it's a multiple choice question. So if you know you're a little bit behind. But if you need to actually find those points, anything you do from the graph, you're going to go to F5, which is here. And so, like, say we're trying to find this maximum point right here. You would just choose maximum. And then you want to, it's going to say lower bound, which means you need to go to the left side of where you think that maximum point is. And upper bound means to the right side of where you think that maximum point is. And you can see we get negative 0.25009, which is what we have right there at that point. And I could do a minimum for finding this point right here. What would I need to do to find this point? 0. Okay, we're not going to go through and find all of those for the sake of time, but you can if you want to further confirm that you are correct. But the AP exam has a reasonable amount of time, but not excessive time. So on one like this, I would check like one point and make sure. Like, I'd probably check this one over here that's different. I'd probably find that 0 right there just to make sure that's 1.085 and make assumptions about the rest so that I could move on, because you might run out of time. All right. Okay, let's look at this next one. The function f is continuous from 0 to 16. It's twice differentiable except at x equals 5, where the derivatives are undefined. Information about first and second derivatives is shown in the table above. At what values of x from 0 to 16 does f have a point of inflection? Okay, so point of inflection, what are we concerned with? What are we looking at for point of inflection? Our second derivative, so we're really not using that first derivative line there. It's kind of there as a distractor. And we are looking for where our second derivative changes signs. It does not matter if your second derivative is positive or negative. So we got 5, we got 8, and we got 12. And we go positive, negative, positive, positive. So what would be our points of inflection? 5 and 8. So B would be our answer there. Okay. First derivative is there as a distractor. All right, now here are some problems where you got to do a lot of reasoning whenever they ask you to find the derivative. They give you a graph. They ask which one could be the graph of something. So, in this case, they have given us f prime. So, f prime is our derivative. They are asking us to find the function above it, f, not the derivative. So this looks like a quadratic to me. So if my derivative is a quadratic, what was my original function? A cubic. So, and my derivative of my first derivative would be linear, right? My second derivative would be linear. So you want to throw a out because a would be the derivative of this graph, not the one that's above it, right? So I feel like it's probably C or B, although there may be some potential for D, maybe. But I'm thinking B or C. So let's think about what's happening here when my graph right here is negative here and negative here. What does that tell us about the original function? Okay, f should be decreasing whenever my derivative is negative. So, does B decrease on this first interval right here? No. Does C? Yes. Right? So we're kind of corresponding here. This right here is decreasing on the same x intervals here that this derivative is negative. Right here, I'm also decreasing, my derivative is negative. In the middle, right here, I have a positive derivative, which means that here in the middle, I should be increasing. So that confirms, right? This one's kind of similar, but I increase the whole time right here, so that's not it. I can also think of concavity if I need to, right? So this function is increasing, right? So if f prime of x is increasing, what's that tell us about f double prime of x? It would be positive. What does f double prime being positive tell us about the original? Up, right? So are we concave up here? Looks like it, right? And then over here, we're decreasing. If my derivative is decreasing, then that means its derivative would be negative. Second derivative would be negative. Would be concave down. And it does appear to be concave down. Now, you could probably choose this one without considering concavity, but it's still like an extra help to confirm that you are correct. And we are out of time, so we're not going to do these last two. We might try to do one of those as a warm-up. So, the assignment, let me see what it is. I think it's on Canvas today. Okay, it's going to be on Delta Math. So, let me show you what it looks like as you pack up. Okay, and I'll probably cut this back so it's not 15. I think that'll take a little while. All right, so it's going to give you a graph. This gives me the graph of f, and you're supposed to answer here. So, on the graph of f, it'll ask you these things from 2 to 4. So 2 to 4 right here. The graph is negative, it is decreasing, and it is concave down. This is actually asking you about the function f, right? Then it's going to ask you conclusions from that. So from 2 to 4, f prime, so f prime from 2 to 4, the derivative, since we're decreasing, it's going to be positive And since we're concave down, it's going to be, let's see, we're decreasing, which means first derivative would be negative. Sometimes I have to write out the chart. F prime is decreasing, which means first, or F prime would be negative, and concave down, so F prime would be decreasing, so negative and decreasing for that. So try these. I'm going to cut it back so you don't have quite as many since we didn't get to them in class. So I'm probably not going to give you a lot of these. We may do a few extra in class. Yes. Yes.
So that chart, like, is it possible for it to be like interchangeable? So like, if it's your original function is concave up, then like first derivative is positive, second derivative is first derivative is increasing, second derivative is positive. Could you like change that around, like switch them out, and it still work?
It pretty much always goes in that direction, but like sometimes, so the chart itself doesn't change, but the information you know and how you're applying it.
Yeah, is
change.
that interchangeable?
Yeah, so like if you know the second derivative is positive, they might not ask you about the original function. They might ask you about the first derivative. So you could say, oh, the second derivative is positive, so the first derivative will be increasing, right? Or they might give you the original function and say, you know, where is the first derivative positive? So then you would be looking for like where that function is increasing. That would mean the first derivative would be positive. So the information they give you changes, and it changes how you use the chart, but the chart itself does not change. Does that make sense?
Yeah.
Okay. You're welcome. Let's see. Let me cut the recorder off, and I'll look for that for you.